So for this part, we prove the fundamental theorem of calculus, meaning the first statement and also the second statement. Okay, so we recall last time we did the mean value theorem for integrals. So the statement is if a function f is continuous on the closed interval ab, then we can find a number c in between the interval ab, inclusive of a and b, such that if you evaluate c in the function, so you have f of c, we will get the average of the function. Okay? Or this f of c is equal to 1 over b minus a, integral of f of x dx from a to b. Okay? Or equivalently, we have the integral of f of x dx from a to b. That's equal to your f of c equals b minus a. So let us prove this theorem. Okay. To prove this, we recall the following. So recall the intermediate value theorem from your calculus 1. So this is your IVT. Okay. The intermediate value theorem. So what is that intermediate value theorem? So let f be continuous on the interval AB. So let f be continuous on the closed interval AB. Okay. Then let small m, okay, let small m be the smallest value of f on AB, be the smallest value of m, smallest value of f on AB, and also we let capital M and capital M be the largest value of f on AB, be the largest value of f on the interval AB. So this means that, okay, let's just write it here. This means that the value of f of x will be less than or equal to m. The value of f of x will be greater than or equal to small m, but less than or equal to capital M for all x inside a b. Okay? These values here, this is small m and this capital M, these values will exist because your function f is continuous. Okay? Take note of that condition. Your f must be continuous on the closed interval AB. So these values here, small m and capital M, will exist. So what is the conclusion of this intermediate value theorem? For every, okay, um, for every k, okay, for every k between small m and capital M, okay, for every k between small m and capital M, okay, there exists a C, there exists a C inside the interval AB such that this f of C is equal to K. So this f of C, this is equal to K. Okay? So graphically, okay, graphically, if you have the function here, okay, and you have, well, this is your axis, and you have this function here, which is continuous on the interval AB. This is your A, this is your B here. So you have this maximum value. Maybe it's somewhere here. This is your capital M. And then we have the smallest value. Okay. It appears here. This is your small m. Okay. So whatever k you choose between small m and capital M. So maybe your k is here. Okay. Then you will be able to find a c inside A and B, okay, such that this point here, this is the point C, comma, F of C. So that's your intermediate value theorem. And I hope you remember that that's from your calculus 1. Okay? Now, we are not interested on the proof of this. Should have been given to you in your calculus 1. So we will prove the mean value theorem for integrals, and we will use this in the proof. Okay? So now, let's have the proof of the mean value theorem for integrals. Proof. Of course, it is given here that your f is that your f here is continuous on the closed interval AB. So we will have that maximum value and minimum value of f. Okay, so um, let small m and capital M here be the minimum and maximum, minimum and maximum respectively. Okay, so let these two numbers be the minimum, maximum respectively, values of f on AB, of value of f on AB. And again, this only says that your f of x, this is greater than or equal to small m, but less than or equal to capital M. Okay? Then for all x here, for all x inside the interval AB, your f of x is between small m and capital M. Okay? So what we're going to do is to integrate this. We integrate this on the interval, over the interval AB. So thus, we have the integral from a to b of m dx. This will still be less than or equal to the integral from a to b of f of x here dx, and still less than or equal to the integral from a to b of capital M dx. And remember one of the properties that we had last time, okay? For this guy here, it's just your small m times b minus a. This is less than or equal to the integral from a to b of f of x dx. This is less than or equal to capital M times b minus a. Okay? Okay? But what we actually need here is, well, let's divide everything by b minus a. Okay? Let's divide everything by b minus a. Thus, we have the following. So let me just put it here, continuation. Thus, you have small m, this is less than or equal to 1 over b minus a integral from a to b of f of x dx, this is less than or equal to capital M. Okay? So far, so good. Again, this small m here, it's the minimum value of f, okay, on the interval AB. This capital M here, it's the maximum value of f on the interval AB. Furthermore, this guy here, this integral of f of x dx, this is just a number, okay? You divide it by b minus a, it's still a number. So this whole guy here, this is just a number. We can look at this as the number k in this intermediate value theorem. Okay? For every k between small m and capital M. Okay? And in here, your k here, it's small there. But anyway, your k here, it's between small m and capital M. So we can treat this number here as the k. It's between small m and capital M. So what does this mean? By the intermediate value theorem, so by the intermediate, so by the intermediate value theorem, okay, there exists a C. So there exists a C inside the interval AB such that if we evaluate this C on the function f, we will get K such that f of C, this is equal to K. Sorry, that should be K there. But this K here, it's this integral. 1 over b minus a integral from a to b of f of x dx. And that's what we want. That's the conclusion of this theorem. So we just proved the mean value theorem. Okay? So why did we prove this mean value theorem? Because we will use this in order to prove the fundamental theorem of calculus. More precisely, we will use it to prove this first statement of the fundamental theorem of calculus. Okay? So, let us prove this. Proof. So in here, you have your function f to be continuous on the closed interval AB. And then we are defining this capital F of x to be this function. Okay? It's the integral from a to x of f of t dt, where x here it's between a and b, including this a and b here. So the theorem says if we have this, then this function here, it's continuous on the closed interval AB. And furthermore, it is differentiable on the open interval AB with derivative capital F prime of x, that's small f of x. Okay? So how are we going to prove this? We will start with the derivative of capital F. Why? Because if we proved that capital F is differentiable on the open interval AB, then it is definitely continuous on the open interval AB. So once we have done the differentiability on the open interval AB, it will follow that it is continuous also on the open interval AB, and therefore we just need to check whether this function f is continuous at the endpoints, x equals a and x equals b. And for those two, again, we'll just have that. It will follow immediately. Okay. So we will start with the derivative of capital F of x. Okay. So for this, what we're going to do is the following. So in here, let's um let's start with let delta x be greater than 0. Okay. Actually, let's start with getting an x. So let x be in the interval, open interval AB. Okay. So let x be in the open interval AB. Okay. And then we will calculate the following. One has, we look at f of x plus delta x, okay, minus f of x. Okay. We will calculate this guy here. Okay. And of course, in here, our delta x here, it will be very, very small, such that your x plus delta x, it's still inside the interval AB. Okay? So in here, one has for delta x greater than 0 with x plus delta x still inside the interval AB. Okay. This guy here, f of x plus delta x minus f of x, well, this is our function capital F of x. So all we need to do is to change this x here or this x here by x plus delta x. And take note, because of this assumption here, x plus delta x is still inside the interval AB. It means that we can do that. We can replace this x by x plus delta x. Because this function here, this is the definition, provided that this x here or this x here, it's between a and b. So we are assuming x plus delta x is still between a and b. So we can have that. And if we do that, this is just the integral from a up to x plus delta x of f of t dt. Okay. And then minus, of course, your x is between a and b, so we'll just copy this function here. So minus integral from a up to x of f of t dt. If we rewrite this, this is just the integral from a up to x plus delta x f of t dt plus integral from x up to a of f of t dt. Sorry, this guy here, this is dt. And now, you see this? X up to a and then a up to x plus delta x. And then you have the addition here. So you can combine this into a single expression or a single integral. This is just the integral from x up to x plus delta x of f of t dt. Okay? And then what we're going to do is to divide everything by delta x. Okay? Divide everything by delta x. So we have here f of x plus delta x minus f of x divided by delta x. Well, this is just this guy here, okay? This guy here over delta x, correct? So you have here 1 over delta x integral of the integral from x plus delta x, or integral from x to x plus delta x, f of t dt. Okay? The left-hand side, if we pass to the limit as x approaches 0, what will happen to the left-hand side? The left-hand side will just become the derivative. Remember the definition of derivative? The limit of f of x plus h minus f of x over h as h goes to 0. That's your f prime of x. But instead of h, I used delta x, but whatever. So we will take the limit of this as x goes to 0. And therefore, we will get the derivative here. Okay? So if you look at this, okay, if you look at this, since your f is continuous on the closed interval AB, and both x and x plus delta x are inside the interval AB, this means that your f is also continuous on the interval x, comma, x plus delta x. Okay? So let me write that. Okay? So since x and x plus delta x, these are inside the interval AB, actually open interval AB, okay? And f is continuous on that closed interval AB, okay? F is also continuous. F is also continuous on the interval x, comma, x plus delta x. Because these two numbers, they are just inside the interval AB. So it's like you have this, let me write it. It's like you have this interval, this is your A, this is your B, your x is somewhere here, your x plus delta x will be somewhere here. We are assuming that x is, or we are assuming that delta x is positive. So x plus delta x will be on the right of x. So if f is continuous on this big interval, definitely your f is continuous on this small interval. So that's what we have in here. Okay? Now, f is continuous on the closed interval AB. We now invoke the mean value theorem for integrals, but instead on the interval a comma b, we invoke it in the closed interval x comma x plus delta x. So what does the MVTI say? By mean value theorem for integrals, by MVTI, there exists a number C. This number C is inside this interval because we are just looking at this interval here. So we have a number C inside the interval x, comma, x plus delta x, such that if we have the integral of what? X up to x plus delta x of f of t dt, okay? This is equal to f of c times x plus delta x minus x. So this guy here, it's your b minus a in the theorem. But x plus delta x minus x, this is just your delta x. So this is just your f of x times delta x. Okay? So, what will happen? So, we now have capital, we now have capital F of x plus delta x minus capital F of x divided by delta x. This will be what? 1 over delta x. And then we go back to this integral here. Okay, this integral here. It's just this integral. In here, it should be f of c. This guy here should be f of c. Okay? But anyway, so this integral here, it's f of c times delta x. So f of c, and then in here times delta x. So this is simply f of x, f of c. Okay? Questions? Okay. Now, we're almost at the end in here. Let us look at C. Let us look at this C. We know that this C is between x and x plus delta x. Okay? Okay? Since C, this is greater than or equal to x, but this is less than or equal to x plus delta x. Okay? Letting delta x approach 0, what will happen to this guy here? Take note, it is the delta x that goes to 0. Okay? Letting delta x approach 0, okay? 1 gets x less than or equal to c less than or equal to x. Meaning, when you let your delta x go to 0, the c is just your x. Okay? Or here, or x or your c here approach x. Okay? Therefore, f prime of x here, this is equal to the limit as delta x goes to 0 of f of x plus delta x minus capital F of x divided by delta x. This is by definition. This is the definition that I recalled earlier. But what is this expression here? So in here, you have the limit as delta x tends to 0. This expression here, that's f of c. Yeah? f of x plus delta x minus f of x over delta x. That's your f of c. So this is the limit of f of c as delta x goes to 0. But again, from here, as delta x goes to 0, c will approach x. And that's why we will have here f of x. So capital F prime of x equals small f of x. That's this part. Okay? So f is differentiable on AB with capital F prime of x. This is small f of x. Okay? Questions so far? Now, this part tells us that your f is continuous on the closed or on the open interval AB. So this part, it's just this end part here. Okay? Thus, capital F is also continuous on the open interval AB. That's from your Cal 1. If a function is differentiable on an interval, on an open interval, it must be continuous on that open interval. So now, to show the continuity at the endpoints, we'll just have the limits. Okay? So now, we want to find the limit of capital F of x as x goes to a from the right. But this is what? The limit as x approaches a from the right. Capital F of x, it's this function. So this is the integral from a to x of f of t dt. As x approaches a from the right, this is just the integral from a up to a of f of t dt. And since your f is defined on a, because it is continuous on the AB, on the interval AB, including A and B, this guy here is what? This is f of A. This is one of the definitions of our definite integral. Let me pull that out. Let me pull the slide pertaining to that. Okay? So it's this definition. If f is defined at a, then the integral of f of x dx from, sorry, why is this 0? Oh yeah, this is 0 in here. Wait, why is this? Yeah, this should be 0, but why do I put that it's your f of a? Huh. Oh yeah, so this is equal to 0. This is equal to 0. Okay? So this must be equal to 0. It's not f of a. Now, how do I show that it's actually your it's the value of f of x at a? Well, we are not interested. Yeah, that is not f of x because, or that is not f of a because um it's the value, the small f of x, it is the derivative of your capital F prime. Okay? So, what is this? What is this saying? You have here the limit of capital F of x as x approaches a from the right. So, if we replace this capital F of x by this, okay, by this will be replaced by a. But by definition, this is what I actually need. By definition, this is capital F of A. Yeah, if I replace this by A, this is A here. So the limit of capital F of x as x approaches A from the right, it's capital F of A. And that's your continuity at x equals A. And then similarly, you have the limit as x approaches B from the left of capital um, F of x. This is the limit as x approaches b from the left of the integral from a to x of f of t dt. And this is equal to the integral from a to b of f of t dt. And this is precisely your capital F of b. Okay? And therefore, f is continuous on the closed interval. So before, we just have the open interval. Now we have the closed interval. So f is continuous on the closed interval. And therefore, this theorem here is now proved. The first statement of the fundamental theorem is now proved. Okay? Now, let us prove the second statement. This is the second statement of the fundamental theorem. If small f of x, small f is continuous on the closed interval AB, and capital F is any antiderivative of f on AB, meaning this capital F satisfies this condition, okay? Capital F prime of x equals small f of x. Then this guy here is satisfied, meaning we have this evaluation of the definite integral. Okay? But now, this theorem here is straightforward since we have proven the first fundamental theorem of calculus. So we will just use this. Okay? How? We will take this function. Okay? We will take this function, and because of the first fundamental theorem of calculus, it has this property, capital F prime of x equals small f of x. And therefore, this capital F here, it's an antiderivative. Okay? The condition of the antiderivative, it's this guy. And the function here is precisely, uh, the function here precisely satisfies that condition here. So for the proof of this, okay, by, well, we take the function. So we take the function capital F of x. We take the function f of x defined on the interval AB by capital F of x. This is the integral from a to x of small f of t dt. Okay? Then, by the first fundamental theorem of calculus, which we just proved, okay, capital F prime of x equals small f of x on the interval, on the open interval AB. Okay? And therefore, capital F here is an antiderivative. Take note that this statement, you can take capital F to be any antiderivative. We just need one antiderivative. And this is the one we need. Okay? By FTOC1, capital F prime of x equals small f of x on the interval AB. Okay? So, capital F is an antiderivative. Antiderivative of small f. On, of course, we just have the open interval, but we can push this to the closed interval. Okay? We can push this to the closed interval. Okay? Okay? Because, well, you have your f. So since f or capital F is continuous on the closed interval AB, again, that's by the first fundamental theorem of calculus 1. Okay? So by FTOC1, that's one of the conclusions. Okay? We have capital F of B minus capital F of A. And the definition of capital F, it's this guy here. It's the integral, okay, from A up to B of f of x or f of t. Okay, let us use that t there. F of t dt minus integral from a to a of f of t dt. And this is where we use the fact that this definite integral here, this is equal to 0. So here we have the integral from a to b of f of t dt. And take note, t here, since this is now definite integral, t here, it's a dummy variable. So you can replace it by x or by any letters. And that's the proof of your second statement. And now we can abuse this method here. So if you are asking for the application of this, well, we have been using it. we have been using this definite integral thing. Okay? Except that we didn't prove it before. But now, we are 100% sure that what we are doing is actually correct. Okay? Questions? Now, look at this. For this guy, okay, for this guy, we proved this theorem using the first fundamental theorem of calculus 1. Okay? So, in here, what we actually have is if we assume the first fundamental theorem of calculus 1 to be true, okay? If we assume first fundamental theorem of calculus 1 to be true, then the second statement, okay, the second fundamental theorem of calculus will also be true. So assuming FTOC1 to be true, FTOC2 will also be true. Okay? So let me just write that. The proof is finished, okay? So don't be confused. The proof here is finished, okay? So in here, we have the following. 1, if FTOC1 is true, then FTOC2 is also true. And we showed the proof. That's this proof here. We assume FTOC1 to be true because we are using it. Okay? And we have shown that this statement is true. The other statement is the following. If FTOC2 is true, then FTOC1 is also true. Okay? Remember when we proved FTOC1, we used MVTI. We used mean value theorem. The reason is we have proven MVTI to be true. So we can use that. So we proved FTOC1. We didn't use FTOC2 because we haven't proved it. Correct? We didn't use FTOC2 because we didn't prove it. On the other hand, when we prove FTOC2, we used FTOC1 because we have proven FTOC1 to be true. That's this first statement here. Okay? But now, what I'm saying is, if you also assume FTOC2 to be true, you can actually prove FTOC1. Okay? If you assume FTOC2 to be true, you can actually prove FTOC1. That's the combined version of the fundamental theorem of calculus. It means that both of them must be true or both of them must be false. Okay? So that's the combined fundamental theorem of calculus. So for you, okay, I want you to do this. I want you to do this part here. You will only assume that FTOC2 is true. You will assume that this guy here is true. Okay? Then how do you prove FTOC1? Okay, so you will assume FTOC2 to be true. How are you going to prove FTOC1? You may or may not, actually, you may not use the MBTI because, well, definitely, if you use your MBTI, you will be able to prove this FTOC1 without using FTOC2. But this time, what if your only weapon is FTOC2? Or you don't have the MBTI card. You only have the FTOC2 card. So how are you going to use this card or to use that card in order to prove FTOC1? I will leave that to you. You can search on that on the internet. Maybe I'll give you a hint. Just search Fundamental Theorem of Calculus combined form and you will see the proof. Okay?